boogie woogie music far, far away. And you know what they say in show business? Lights, camera, action. Alright, I guess that's what we are trying to get here in the midst of all this excitement. Alright, ladies and gentlemen, I will sit here and talk quietly while he waits for the music to fade down. Okay, that was a nice fade. Alright, I'm going to take off these sunglasses here so I can be exposed to the real lights. Alright, we are in the lower quarters of City Hall in the Channel 10 facilities, and there we have cameras in front of us, and we have lights and everything. And we tried to make it look like it's a classroom here, and I have 50 of my star students here in front of me, but in reality, it is all just kind of staged at City Hall. But you don't have to know that. Just pretend that this is a lecture for you at the university level, and you have paid hundreds and hundreds of dollars to sit in on this lecture. Not really. We try to keep it fun here. Well, okay, so, ladies and gentlemen, today, aujourd'hui, on the calendar, it is the last day of September, so it's 9:30, so that when I make reference to the kind of the Where Are We segment, you'll have an idea of where we are and what we're going to have in this program here. Watch on the screen where we have the P.O. box for your questions and comments, the program times, and what we're going to have today for you is I'm going to have a couple visuals. I got a kind of a nice picture of the sun I got from National Geographic. And also the people from Office Max gave me a pretty nice poster. And I'm going to show you that, and I told them I'd give them a free plug. But the crux of the show today, they're telling me where to look here. The crux of the show today is I'm going to talk about what they call the Vomit Comet, which is a kind of a older kind of a tanker type airplane, a 707 that's been modified, and they use it for people who ride in this concept of the zero gravity. And what it really is a giant roller coaster in the sky. And I'm going to kind of explain that, and that should be kind of fun. And then the other thing I want to spend a little bit more time when I do the Where Are We segment, I want to talk about the equinox. The equinox occurred, it's the 30th. The equinox occurred about a week ago, and Watchwell didn't do a program around that time. I think the last one was done around the 9th of September. And there were the guys, the weather guys, and they were trying to explain, you know, what the equinox means and how the sun changes on the equator, and even Pat Schneider on the SAU, they tried to kind of get it and kind of reading a script, but they didn't really quite get it. So Watchwell is going to try to clarify that for you, and I hope I will do a little bit better job. So we always have a few things to talk about, but the main thing I'm going to talk about here is a little bit physics. Now, I did threaten you the last time I said that now that school is back in session here, that we're going to kind of pick up the pace on the expected comprehension of my viewing audience. So today I actually am going to spew out like a little bit of what you call, what would you call it? You would call it, I guess, dynamics. We're going to talk about dynamics because in order to understand the concept of zero gravity, there's some things that have to do like with velocity and Newton's second law and so on and so forth. So we're going to kind of pick up the pace here. So kids, no fluffball stuff anymore. You better take notes because there's going to be a test. Okay, having said all that, ladies and gentlemen, he's 3 minutes into the show and he doesn't even pick up a piece of chalk. So what I'm going to do is I'm going to save the Where Are We segment until we talk about the equinox. And so I'm going to do my little visuals, and then we'll start talking about the Vomit Comet. All right, like I said, we got some nice visuals today. This is one I'm going to do maybe a show in the future about the sun, but I got this out of a National Geographic. And this is a close-up here. If you can get this, just go for the effect here, Andy. Just get as much fire as you can here. This is, ladies and gentlemen, a picture of the sun. So just fill her up the best you can, and that's the fiery, burning sun. All right, the big nuclear bomb in the sky. And it's pretty cool. And we'll do a show on that later, talking about how the sun works. And then my other visual, and he's momentarily off camera. And my other visual that I thought is pretty cool is the Office Max people. They had, while people were going back to school and buying all their school supplies, they had these big posters. They had these big, these big posters that they were showing. And they had even bigger ones, and I asked them if I could have one, and they gave me one. And there's a big picture of Albert Einstein. This one, let me put that in a frame and use that one. because I always talk about the emphasis is to learn. Of course, and I'm not sure who this young man is here, but anyway, that's kind of the other poster boy who's the young man who's eager to learn. And Office Max that says, what's your thing? So you can go and get school supplies and use the school supplies to learn. But I mainly asked the poster because I love the picture of Albert Einstein. As you know, we have Albert up here as our ongoing icon for the enthusiasm to learn. So those are my visuals for you today. Okay, so that's kind of fun, right? It's kind of like when you go to school, it was always fun when you had, when you had like movies or something to kind of break up the routine. So that was our visuals. But now, today we are going to talk about, okay, let me get off my other stuff. We'll talk about the Vomit Comet for a while, and then we'll finish up with the Where Are We segment. Where are we? Okay, so now the reason why it kind of struck my attention, again, I was listening on the news. They were talking about the concept of, I caught this on the news, and I thought it was interesting, the concept of okay, so there was a story on the news, and I thought it was kind of interesting, and it's called the concept of zero gravity. And of course, what zero gravity means is the concept of effective gravity is that. See, this is real effective gravity because I'm dropping this, and of course, the force of the Earth is pulling it down, hence it accelerates downward. But now, if we were in a situation of zero gravity, I would let go of this chalk, and it would just kind of, it would just be kind of be floating around, you know, just like maybe, like a balloon, like picture like a party balloon where you would just tap it, and it would kind of dance around. So the concept of zero gravity means that there is no gravitational force pulling it down. And so on this particular planet, on the planet Earth, it's hard to get away from the gravity because the gravity is always there. So the question becomes, how does one attain zero gravity? And the question is, or I should say the answer is that one must be accelerating at a rate greater than or equal to the acceleration of gravity, which on this particular planet happens to be 32.2 feet per second squared. Okay, so here it is. This is kind of like classical physics. So we're going to talk about classical physics today, and this is something that people probably start learning in high school, and then of course you get in depth in college. You get it in physics, and then you get it in other courses, dynamics, and other areas where it gets repeated and refined and more specialized. But anyway, so this is what we're talking about: how we can achieve a zero gravity. Now, probably a real good example of feeling weightless would be like if you were to kind of go into like an elevator shaft and you're walking here and the door opens and you don't know that the elevator isn't there, then you're standing in here and then you kind of probably fall to your death because you go in here and you'll probably feel kind of weightless, but unfortunately you would only feel weightless for perhaps a couple seconds before you hit the bottom of the shaft. But in concept, if you kind of visualize yourself falling kind of in a endless, that's the key word here, if you would visualize yourself kind of floating endlessly in an endless elevator shaft, that would be somewhat the concept of weightlessness. Okay, just so you kind of get the idea. And remember that 32.2 is the magic number in that that's the rate of speed that things accelerate toward the planet Earth. But as I get into my little treatise here, I have to watch my time, into my little treatise on weightlessness, I do have to point out one concept, and I'm going to spend a little bit of time here talking about the Vomit Comet, which is what I said, is a airplane that goes in the sky, you know, like a roller coaster, like a real roller coaster goes, but of course on a much bigger scale, and it's not tied to any tracks like roller coasters at an amusement park. It goes in the sky, and I'll explain that a little bit. But I have to quickly point out a little bit different concept between the Vomit Comet in the airplane weightlessness versus skydiving. And it's important that I point that out, because you would say, well, if you want to feel weightless, just go skydiving and you feel weightlessness. But I have to point that out, that there is a subtle difference between the two. Okay, so again, I kind of warned you that this was going to be a little more, requiring a little bit more mental capacity to stick with Watchwell today. Okay, so here it is, ladies and gentlemen, in 25 words or less. In the, like I said, I saw this on the news about this weightless plane. And then if you want to look up some of the notes that I have, again, I have no special information, go to your Google website. And what I did is I looked up, what did I look up? I put down zero gravity, just the same words, zero gravity, and then I put down plane rides. Plane rides. Okay, that was my search. Nothing fancy. So you just go to your Google search and you go zero gravity plane rides, and then any number. There was about 10, 15 entries came up. And what they do is they talk about these. There's a couple different plane companies that have this thing. And by the way, it's a little pricey. I might point that out. It's a little pricey to tell me. Look, it basically costs about three grand. Okay, it basically costs about $3,000 to go for a 2-hour plane ride, and then you basically get about 30 humps. And how it basically works is, like I said before, is it works like a big giant roller coaster. Okay, so this is like the ground, and where the plane goes. So again, it costs you some money, about $3,000 for 2 hours. And how it works is, like I said, is it's like a big giant plane ride in the sky. And so it goes like this. The plane takes off, and then it goes up way high, and it goes down, and it goes up, and it goes down, and it goes up, and it goes down, goes up, and it goes down in big wild oscillations. And it does about 30 of these guys, okay? And what it does is the plane is flying. Now, it turns out that you got to understand the differences. The flight that it goes to is about 35,000 feet, okay? Which is similar to about the flight ceiling of a commercial airplane. Maybe a little higher. Normally, planes fly at about 32,000. So it goes even like a little bit higher. And of course, then the low end is maybe 2,500 feet. Okay, 2,500 feet, about half a mile. And what the plane does is it's flying. It's like a 707. And they said that they kind of gutted it all out, and they gutted it all out, and they have like just padding on there. And then you get in there, and then they give you like a special jumpsuit and so on and so forth. And the reason why they call it the Vomit Comet is because if any of you have ever been on any rides at the fair and whatnot, you always know that when you go over the hump, sometimes people heave their cookies. And it's the same thing, except perhaps on a more exaggerated way, because instead of being just maybe 3 or 4 seconds of feeling weightlessness and feeling what they say, feeling your stomach and your throat, you're enduring this for approximately 30 seconds. So when the plane goes all the way up to the top, when it reaches the top, it comes back down, this particular distance is about 30 seconds. So it's kind of like a dive bomb. So what it does is the plane is driving along at, say, 300 miles an hour, and then it accelerates 2G, which means twice the speed of gravity, or approximately, like I said before, 32 feet per second, approximately 64 feet per second squared. So it's kind of really diving up. So on the way up, you see these pictures of like the astronauts where they're kind of laying in their seats and they're going like, and they're feeling this force. And then that's kind of like what you're feeling on the way up. You know, the passengers are probably feel like they're getting pressed into the floor going up. But then when they reach the pinnacle of the top, this is like a parabola. Like this is an upside down parabola, and then this is like the right side up parabola. And then when they get to the top, then of course then it goes the other way, and then they're going back down at approximately 2G going down, okay? So then it's about a 2G force going down, and then they're going like here, somewhere from about this point here to this point here, is you have eliminated the feeling of gravity. And I'll do the algebra quickly if I can. To show you why it is, in fact, that you are feeling weightless at that point. So for about 30 seconds, which is really a pretty long time, you're going over here, and then all of a sudden, for that half a minute, because you are accelerating greater than the speed of gravity, you feel this total weightless. And then they show the picture of the people in the plane. They're kind of like doing little springs around and something, all kinds of floating in the air and doing silly stuff because, again, going back to my elevator analogy, they're falling down this kind of endless elevator. So there's some pretty tremendous distances. Now you got to remember that, again, that the plane is pulling way up here, and this is like thousands of feet. So when this thing is free falling, if I have time, I'll show you the math. It's like a couple, three, like from 30,000, it's dropping from about 30,000 down here. It's dropping, you know, about 30,000 feet. It's just outrageous. And of course, when the guy gets to the bottom, he definitely has to pull out the stick and get it all back up. And so it keeps on doing this series. But here's the point where I got to talk a little bit about the difference between this Vomit Comet business versus skydiving. And then this is kind of an important kind of a subtle thing to point out. When somebody is skydiving, you start out at about, I guess they go lower. They go maybe, I think it's maybe only 12,000 feet. They're not quite that high. About 12,000 feet. But then when they jump out of the plane, it turns out that even though the velocity is equal to what they call the acceleration times the time, it turns out that because of the air, this is an important point, because of the air resistance is that when you're jumping out of an airplane, is that your terminal velocity becomes approximately 256 feet per second, okay? And that means that you reach that velocity in approximately 8 seconds, okay? So you fall out of the airplane and you're really free falling, you know, But then because the air, in effect, makes a frictional cushion, you don't just keep on going. Whereas in pure theory of the physics, is that if you have an acceleration where velocity and time, and you have an acceleration, in theory it keeps on going linear ad infinitum. But it turns out that you after about 8 seconds you flatten out. So then what it really looks like is, instead of just keep on going forever, in about 8 seconds you reach a velocity, and then it kind of like just flattens out. Okay. Now, so having said that, see, this is kind of a little more subtle, but this is not hard. What I'd like to do here is like maybe get you guys to ask your physics teacher to kind of talk about some of this stuff, because this is kind of classical physics. Okay, now, back to my Vomit Comet. Now, it turns out that in the concept of the plane going down, okay, in theory, when you're inside the plane, okay, so here's the plane, here's all the passengers inside the plane, and they're going down at this 2G business. Okay, granted, the plane is fighting off like a certain amount of air resistance, but for the most part, because you're going greater than the speed of gravity, you're going down, and in reality, because you're not hitting any kind of an air cushion other than what is going on the outside of the airplane, inside of your particular space, you are achieving absolutely near zero gravity, hence weightlessness. And so it's like pretty kind of cool. I think I'll stop there on this one. I'll just point out one more little thing. So if you want to know more about this, again, go to the search that I went to. It's called, just go to Zero Gravity Plane Rides. And then, of course, the little news releases that I got was, there were some students from different universities that went on this, but they were interested in doing some experiments under zero gravity to see if certain things would behave differently, and so on and so forth. But I was just concerned with just kind of like the raw physics. Let me do one more quick thing here. Again, you could pick out any one little thing, and if you were like a university professor, you could pick out like one little aspect and turn it really into 3 or 4 or 5 problems. And I will do just one. Now, I just want to make sure that you understand real quickly the concept of zero gravity. Now, again, F is equal to ma. That's Newton's law. I'm going to do this real quick. Newton's law, okay, F is equal to ma, and the concept is we want to feel F, we want F to be 0, because that will make us feel weightlessness. So rewriting this, F is equal to, the mass is equal to the weight over gravity, and if the acceleration that we're speaking of is the gravity itself, then these go away, and hence the force, the gravitational force is equal to the weight. That's like if you step on a scale and it says that you weigh 180 pounds, well then the force and the weight equal the same. But now if we want to question the fact at what acceleration will I end up feeling that there is like no weight force on me, it ends up being like just a little bit of algebra, but it all makes sense. So if we say that F is equal to ma, you can rewrite that F is equal to weight over gravity times the acceleration. What acceleration, we're not sure of, okay? But we know it's going to be gravity. Okay, then if you quickly rewrite that, you can say that the weight over the gravity times gravity is equal to weight over g times, again, the mystery acceleration. You can see that everything cancels out. Gravity and gravity goes away. The weight and the weight goes away. And what you're left with is the concept of 1 equals a over g. Therefore, if g is equal to negative a, in theory, your weight will feel like you have none. And again, and that goes back to my free falling, my analogy, that if you're falling down the endless elevator shaft, if you're moving at the acceleration of gravity, there will be no weight. You would be falling down the elevator shaft, this infinite elevator shaft, and you would stand there with a bathroom scale under your feet trying to weigh yourself. You would find out that the calibration on the bathroom scale would be 0. And so it's the same concept. So it's really not that hard. And what I'd like to do again is, kids, if you don't get this, ask your physics teacher or something to explain this to you, and they probably could do a pretty good job. But anyway, go to that Google search and get some information on the Vomit Comet. I thought that was kind of interesting. Okay, now I want to talk, I got a few remaining minutes here. Now I want to talk a little bit about the equinox, if I have a few minutes here. Like I said, the weather guys, they kind of close on. Watch, oh, what's that mean, voice? I'm losing my voice here today. It was the equinox time, which was, again, it was 9/22 was the equinox this year. And the guys didn't really quite get it right, okay? So what they said was, okay, well, today's the equinox. We have equal dark, equal light, and the sun changes on the equator, which is kind of right, but someone should explain it a little bit better. So I got about 3 minutes to do that. So here's what we're going to do. Here's what I'm going to do for you. I'm going to draw 2 pictures of the Earth, and I'm going to point out a couple positions. Okay, as you know, first of all, as a setup, we all know the drill, right, the old Watchwell drill. We all know that the Earth goes around the sun counterclockwise, okay? And we all know that the Earth rotates counterclockwise, okay? So we know that. So that's the setup here. Now, when we get to the equinox and the fall, let's just do it like this. Let's just say that, let's kind of rotate it this way just for the sake of discussion. We're going to say that the planet is here, and if you look at it from the planet from the top, it always looks like this because the planet is always at 23.5 degrees, right? You always know that business, right? They say that the Earth goes around the sun like this, right? The axis, this axis is always at that 23.5 degrees. Okay, so now when you get to the fall equinox, the vernal equinox, if you look at the planet from the top, okay, if you look at it quickly from the top, you can see that the planet is kind of like that. The orbital line is this way, the planet's rotating this way, and at this point, we're going to call this the sunrise, and at this point, we're going to call this the sunset, as the planet is rotating, because the separation, this is what they call the line of illumination, this one here, it's called a line of illumination as the planet rotates from 6 a.m. to 6 p.m. is the light, and from 6 p.m. to 6 a.m. is the dark. So it turns out that in terms on the line of illumination, it is precisely just like taking a piece of pie, excuse me, and just absolutely just cutting it in half. And that has to do with the fact that, again, this 23.5 degrees. So if you would look at it like if I would make like the sun over here at the sunrise and the sun over here at the sunset, this is kind of like what we see, you know, right on what this would be what you would call your equatorial line. And now it turns out that the very same thing happens in the spring and the fall. The spring and the fall, it's the very same thing, except in the fall time, because this is the sunrise and the sunset, then the sun is like on this side of the planet because the planet is going that way. Now, if you would take the same thing and just reverse it to the spring, in reality, it is like this. It goes, if you go 321, the kind of like the orbital line of the planet is, the sun is going this, the planet's going that way, because it's on the other side of the proverbial racetrack. The sun's over here. Then, if you're going to say this whole same business, then you say that this is the sunrise and this is the sunset, okay? But yet it's the same concept, is that you have the sun rises and sunsets appear exactly on the east-west horizon, okay? That's the key word. It's exactly on the east-west horizon. And now, I'm not sure if I'll have to do the other one. Now, that pretty clearly explains what happens in the spring and in the fall. But now, in the other times of the year, of course, what makes it rather interesting is the following. And I'm going to see if I can quickly squeak this out. Okay, I covered myself on the equinox, but now if I can quickly get it on what happens in the other times of the year. And it turns out that the line of illumination changes at different times of the year. And therefore, when, oh, there's my music, oh no. Therefore, in the summertime, the sun comes in like this, hence the sunrises and sunset are above or to the north of the equatorial line, and vice versa when it's afterwards in the fall, then the sunrises and sunset appear to be south of the east-west horizon. We could talk about that a little bit in the future. Ladies and gentlemen, Watchwell is my name, natural philosophy is my game, and I hope you enjoyed your ride on the Vomit Comet. We'll talk to you later. Bye-bye.